To solve for linear displacement, we have to have the original, so the change in x, so the original x position, and this would be subtracted by the final x position. And so that's the same thing is true for our theta. For our angular displacement, we have to have the original, it's the final displacement minus the original displacement. And so to solve for our velocity, well, we need our displacement over time, which is still true for our angular velocity. We have to have the change in theta over time, and still is true for acceleration. We have to have the change in velocity over time, and then we have to have the change in angular displacement, or angular velocity. So there are also a handful of equations that relate linear to angular. So to solve for our linear velocity or tangential velocity, we have to multiply the radius of our object by the angular velocity so that we can solve for the tangential. And then the same is true for acceleration. To solve our tangential acceleration, we need the radius times the angular acceleration. So as the linear velocity and acceleration increase, since the radius is fixed upon that axis point, that means that our angular velocity and angular acceleration will also increase. So moving on to our kinematics, or DVATs, it's a lot of things that are true for a linear kinematics, it will be true for rotational kinematics. So to solve for change in x, 1/2 VF minus VI. So everybody by now kind of remembers these. So to solve for final velocity, we get by initial velocity plus acceleration times time. Change in x, our displacement, is the final velocity times time plus 1/2 acceleration times time squared, and then our final velocity squared equals the initial velocity squared plus 2 times our acceleration times the displacement. And so for rotational kinematics, rotational kinematics, to solve for our angular velocity, let me move it so you can see both, it is going to just be this equation right here. So our final angular velocity will be equal to our initial angular velocity plus our angular acceleration times time. For our angular displacement, we have to have the final angular acceleration times time plus 1/2 angular velocity times time squared. A lot of times. Then the same goes for our final angular velocity squared. So let me just it's the displacement. So we can just substitute our new variables in to get our rotational kinematics. And so all of this is true if we have a constant, that's a really bad start. Angular acceleration. So now moving on to torque. Well, what is torque? Torque is the measure of a force applied to a rigid object from a distance r, which is our radius, around a pivot point. So if we look at this diagram that I have, this drawing, it's a nut and bolt, or it's a wrench and a bolt. So if this is just one object, then as we turn this wrench in the positive x direction, well, we have to apply some force. We have to push upwards so that this can move. And doing so, we're pushing from a distance. So this is our radius. This is the radius r. And this is our force. So our force is perpendicular to our pivot point. So if we're looking at our equation, well, this is just force times radius. It gets us our torque. So that's just radius times force. And well, if we're not pushing perpendicular, well, this isn't perpendicular, we're pushing at an angle. Well, this angle, then our perpendicular force, the vertical one, would just be sine theta. So now we have force times sine theta. However, if it is perpendicular, sine theta, sine times 90 degrees is just 1. So it's just r times f. So if we want to, if we relate this back to Newton's second law, where the net force, we get the net torque. If we want to solve for net torque, we relate this back to Newton's second law, where net force is equal to mass times acceleration net. And so the more force, the more acceleration we have. So that's also true for our torque. So if we have the net torque, we get when we plug in our force, we get r times ma. And well, we know acceleration from our derivation. We get acceleration equals radius times angular acceleration. The net torque equal to r times m. Don't forget the mass times the radius times angular acceleration. Well, if we just neaten that up, that's torque equals mr squared, mass times radius squared, times angular acceleration. And well, from previous units, we know that that is our rotational mass. So this can really be summed up to our rotational mass times angular acceleration. So as our torque increases, as we apply more force, our torque increases, then our angular acceleration also increases. So that's just kind of like a quick recap of everything we've learned.